the Weil group. So remember, what did that say? So maximal torus theorem. And the Weil group. So given G compact, there exists, we can formulate in two ways, a T in G, which is a maximal compact and abelian, or equivalently a T inside G, which is a maximal abelian subalgebra. Where then, of course, the Lie algebra of the maximal torus is the maximal abelian subalgebra. And one statement was that if I take if I take the adjoint orbit of the Lie group of any vector in the Lie algebra that intersects T, in the Lie group version, it would be if I take an element in G, and if I look at the orbit, if I look at conjugation, so every element in G is conjugate to an element in the maximal torus. So right on the Lie algebra level, it's adjoint. On the Lie group level, would be conjugation. So I can always conjugate something into the maximal torus. Okay. And then the other statement was that we have the Weil group, W of the Lie algebra G, of the Lie group G, was the normalizer of the torus divided by the torus. We actually proved that the centralizer of the torus, T, was equal to T. This was part of the statement, so it's normalizer mod centralizer, if you want to, and this acts on T. So if G is a normalizer, right? Well, let's call it N, distinguish it. If N lies in the normalizer, then N times a vector X is just, well, I think the notation I want to use is maybe the Weil group. So let's start like this. If I take a Weil group element in W, then that means there exists an element in the normalizer whose coset element is W. Right? So if you want to N times T is equal to W in the quotient. I'm not going to distinguish those letters anymore. And then it acts via adjoint. So X goes to at Nx. When X lies in the maximal abelian subalgebra. That's well defined because if I modify it with something in the maximal torus, it acts trivially. Torus was a centralizer. So this is well defined no matter what coset element I take. So W acts on the maximal abelian subalgebra. Then the statement was that if I look at an adjoint orbit of some vector x, say x lies in the maximal abelian subalgebra, then it intersects the maximal abelian subalgebra precisely in the Weil group orbit of x. Right. So x lies in my maximal abelian subalgebra, W acts on it, so it takes x to other vectors inside the maximal abelian subalgebra. This all lies in T. We also proved W was finite, so it's a finite group. So there are finite many elements in this orbit, and that's how often the adjoint orbit intersects this maximal abelian subalgebra. So that was a statement. Particular one way we're often going to use this, I can formulate as follows. Say, if at G x equals to y, where x and y are in the maximal abelian subalgebra, this implies there exists an W in the Weil group such that W times x is equal to y. Because this is the same adjoint orbit. Right? So then they must be equivalent by an element Y group. So usually, in fact, this is how we use it. Important property of the Y group. We had an example last time I want to do one other one. G was the unitary group. So then the maximal torus were just the diagonal matrices. I'm going to also denote this often by diagonal of Z1 up to Zn. So I don't have to write down such a bit matrix anymore. Right. And of course, here the Zi's are unit complex numbers. So this is indeed a circle n times. Right. So it's an n torus. I can put the dimension here if I want to. And then W, xy permutation. Of the Zi's, so the components of the diagonal matrix. So in particular, W is then isomorphic to the permutation group at n layers. Right? And the same thing is true if I just look at the SUN sitting inside UN, where the only additional property is, of course, that the product of the Zi's must be equal to 1. So it's a subtorus. Right? So in here I have an n minus 1 torus, which is a maximum torus, not an n torus. Right? But the Weyl group is still permutation. Weyl group doesn't get smaller just because I take a smaller subgroup. In this case, right? Still permutation group. Okay. So what these Weyl groups all look like for all the various Lie groups is an important question. Okay. Okay, another comment we made, which I maybe should repeat in the next example. So if I look at, say, let me write it like this. Then each adjoint orbit has a unique element of the form theta 1 small to theta 2 small to theta n. So I can just order the theta i's by using the Weyl group, right? Adjoint things in the Weyl group orbit, like in the adjoint orbit. I just change them, so it look like this. And this is unique. Each one has a unique one like this. And then we also argued what do the orbits in general look like? What's at G of such an element X? It was the form UN, right? UN acts on it, and the stabilizer was UN1, UNK, where summation Ni is equal to N. So that's what all the adjoint orbits look like in the unitary group. So very nice description. This is also what one calls a flag manifold. So there's another way to look at this. So let's look at the flags. So again, prescribe these integers. Right, they're k integers. By flag, I mean the set of subspaces, V1 inside V2, inside Vk, inside Cn. So set of all subspaces where the dimension is prescribed. And let's see, n1 should be this dimension of the first subspace. Let's see how that should go. n1 should be dim v1. But I'm fixing these numbers. So I'm looking at all n1 dimension subspaces. The next block should be my n2. So what's dim v2 should be n1 plus n2, I guess. Or better way to say it, maybe since n1 is dimension of v, it's like the codimension, and so on. But anyway, so I'm prescribing numbers, the dimension of the subspaces, and I look at all subspace one is contained in the other. That's called a flag. So these kind of flag manifolds are very important. And it's not hard to see that the unitary group acts transitively on the flags, because it acts transitively on all the frames. Right? And that's the stabilizer of a flag. And I can do anything in V1, anything in V2 orthogonal to V1, and so on. So all the adjoint orbits in UN are just flag manifolds. Like sometimes adjoint orbits are called flag manifolds for any Lie group because of that. But, it's really only justified in that case, kind of. So maybe an interesting case that I still want to do is SO2n. The other ones I'll leave it up to you. So what should a maximal torus be? So the analog of such a block matrix, right? So of such a diagonal matrix. Of course, there's nothing in SO2 that's diagonal, so I take a rotation. And so on. So I can take, I guess, n rotations, right? The last one is theta n. Right, each one is the usual 2 by 2 rotation. The minus I put there. So all these 2 by 2 rotations written down in a block. They certainly commute, right? Everything commutes with each other. That's commutative. It's just a circle, and these have nothing in common. It's commutative. So this is isomorphic to an n torus. Of course, your theta n should go from theta I should go from 0 to 2 pi. Of course, 0 and 2 pi is the same thing, so it's really a circle. And then the claim is that Tn is a maximal torus. What's the easiest way to do this? Probably something analogous to what we did over here. So how would you argue that this is a maximal torus? So you want to show that if something commutes with that, it must lie in it. So how would you do that? Pardon? With eigenspaces, so they're like, well, see, of course, there's no real eigenvector. Since it's orthogonal, there's no real eigenvector. But there's this 2 by 2 invariant subspace, if you want to, right, on which the thing acts by rotation. Choose all the angles different, right? It has to commute with everything where all the angles are different. These are preserved here. Anything that commutes with it must preserve them again. So it must be of this form here again. Of course, then here it must be rotation. A 2 by 2 orthogonal matrix, only rotation. So again, argue via eigenspaces before. While groups a little bit trickier. So if I claim the following. You have permutations in the theta i's and an even number of sign changes. So let's see why it should be an even one. So let's do the following computations, kind of similar to what we saw over here, why sign changes, why permutations had to lie in it. Let's take a matrix of the form 0, 1, epsilon 0. Epsilon is going to be plus or minus 1, depending on what we want to do. And let's see how it conjugates a general 2 by 2 matrix. So if you compute that, what you get, I'm going to carry it out. Let's see. D, A, and the off diagonals one are epsilon c and epsilon b. So that's a computation. Like, so in this case, for example, what would you say there? Of course, notice that the determinant here is minus epsilon, right? This 2 by 2 matrix. So it doesn't necessarily have determinant 1s. That's something we have to worry about in a minute. Right? But if I choose b and c equal to 0, so if I have one of these diagonal matrices here, it just switches the 2, no matter what epsilon is. Of course, I can choose epsilon d minus 1 that has determinant plus 1. So it lies both in U and also in SUN if I want to. Right. So this was the argument for why the permutations lie in there. You can choose a matrix like this. So let's apply this to a rotation. So what happens with a rotation? Diagonals are switched. That doesn't do anything. Cosine theta, cosine theta. Off diagonals are switched, but I pay with a sign. So this becomes, where is it? Epsilon times sine, and then minus epsilon sine. So that's the new matrix. So let's think about what that means. I'd like to say I can change the angle. So notice, for example, when epsilon is minus 1, it doesn't do anything, right? Then it's the same matrix. So I'd like to choose epsilon equal to 1. Then, of course, this becomes sine. This becomes minus sine. And that's the same thing as a matrix, but with angle minus theta. So in this here, it takes, when epsilon is 1, then r theta gets taken to r minus theta. So I'm changing the sign of the angle. Right? But there's a problem because when epsilon is 1, the determinant is minus 1. Right? And I can't do that because I want to be in the connected Lie groups. I want to be in SO2n. Right? So I can't just change a single sign. But what I can do, I do it twice. So then what I want to conjugate with is 0, 1, 1, 0, 0, 1, 1, 0. This changes sign, so theta 1 goes to minus theta 1. Theta 2 goes to minus theta 2. And now the determinant is minus 1 times minus 1 is plus 1. So this element lies on SO2n. And similar for any combination of two of them. So I can change an even number of signs. Okay. Permutations are a little bit trickier. I think the matrix I wrote down the notes is actually wrong. I believe it's something like this. We're not going to do the computation. So you have a rotation here, because these are 2 by 2 blocks, they're 0 in the original matrix. And what would I like to conjugate with? 0, 0 here. And I want to copy this matrix kind of, which permuted to entry, which in the case of U and permuted to entries. I think it's something like, that's my guess, that if you conjugate with, it takes this one, switches theta 1, theta 2. Permutation on these two. It's possible that it has to be a 1, 1 here, or 1, 1 here. That's the only two I don't remember anymore. I think in the notes it's wrong. Anyway, there's a small computation you can do. So I can do any permutation, and here's an example just, that generates a permutation group. And then I can do an even number of sign changes. So what's W? W as a group is isomorphic to the permutation group. And then I have Z2 to the n minus 1. Right, Z2 would be any sign change, but it has been even 1. So Z2 to the n minus 1. And do they commute? That's a good question. Do they commute? They should, right? If I permute, if I first change signs and then permute, I first permute and then change signs, shouldn't matter. So they must be the right product. So that's the while group in this case. And just we can indicate what changes if we do SO2n plus 1. There's one idea that changes. So, of course, in this case, what should the maximal torus be? Again, rotations. Then I have one more. It should look like this, and so on. So I add one more. That's, again, the maximal torus. Notice that this is, again, n-dimensional. This here was also n-dimensional. Remember, that means the rank of these groups are the same. Right, the dimension of the maximum torus was a rank. It's equal to n in both cases. Again, permutations, the same thing, but just ignore the last coordinate. So W certainly contains permutations. That's clear, as before. It certainly contains even number of sign changes, but just ignoring this. But I claim now I can change any sign individually, because I can just do the following using my extra column. Let's say, let's do it for a 3 by 3 just to get the idea. Here I have rotation by theta 1. I want to change theta to minus theta. So what matrix could I take? So I'd like to use the one we did before. Which one was it? Epsilon equal to 1, right? So 0, 1, 1, 0 in here. That's going to change the sign of theta. The term is minus 1, so just adjust. I have an extra column. This is determined 1. And takes theta to minus theta. So here it's any sign changes. So there's a small difference in the while groups between SO2 and SO2n plus 1. That's important. It's a good exercise to think about what are all the while group orbits. A little more tricky than the unitary case. Just flag the kind of analog of the flag manifolds contained again, but there's one more. We should maybe do this as an exercise at some point. Okay, so these are all the examples. So now we want to go to complexify, understand the Lie algebras, the complex Lie algebras, and then come back to the real ones. So say, if G is compact, then we call the G algebra G compact. Then we showed that G was isomorphic to the center of G. Direct sum of ideals with G comma G. But this was semi-simple. So in particular, it's sufficient to understand semi-simple ones. So we start with a G real Lie algebra, which is semi-simple. And then we complexify. This will be a complex Lie algebra, of course. And one of the exercises was that if I look at the killing form of the complexification, restrict that to G, it's just the killing form of G. So if you want to, what that says that if I were to write down a real basis of G, that's also a base of complexification, a complex base of that, and the matrix B has the same form. Right? This implies it's also semi-simple. So complexification of semi-simple algebras, real ones are semi-simple. So from now on, we're just going to look at semi-simple real ones. Try to understand them. Classify. So G complex semi-simple. At some point, we could even assume that G is simple. But it's true again that G is uniquely isomorphic to G1 plus Gk, where Gi are simple, just like in the real case. So eventually, we can assume G is simple, but for the moment, it doesn't really matter. So we're not going to do that yet. But eventually, in the classification, that's what we're going to do, assume it's simple. So then the analog of a maximal abelian subalgebra is a little bit tricky in the complex case. It's called a Cartan subalgebra. If, and now I need two conditions. One, H is maximal abelian. And the other condition is that if I take an x in H, then ad x is diagonalizable. Which is also, of course, a semi-simple. So an anamorphism is called semi-simple if you can diagonalize it with respect to some basis. So there's extra condition that I can diagonalize these, which in the case over here, I claim I don't need this. So if I have a compact semi-simple algebra, of course, then in here I have my maximal abelian subalgebra. At x in this case is q with respect to an inner product, because I have the killing form. It's a skew-symmetric endomorphism, because it doesn't diagonalize. That doesn't make sense over the reals, as this 2x2 form. But I complexify, it diagonalizes. So at x on G tensor C is diagonalizable. So there's no problem when I think of compact leaves and complexify. It's not a condition. But if I just think of semi-simple complex Lie algebras, one needs the condition B. Let me see what an example is. Probably SL2C already. Things must go wrong. So what should I expect H is? What should H be? What dimension, what form? Well, from our experience, should be diagonal, right? Similar R should be diagonal matrix. But there's an extra condition. The trace is 0. Right, so diagonal matrix, trace 0. So this is A, this is minus A. Of course, A is now a complex number. Right? Particularly the rank of this Lie group, of this Lie algebra, is equal to 1. And so a generator would be this generates this maximal abelian subalgebra. And now I just have to convince myself that ad x is diagonalizable. That's the extra condition I need for something to be a, a maximal abelian. So why is that diagonalizable? Well, I can just see what it does on a basis, I suppose, right? What's the basis of GL2C? Of course, the element in the maximal torus, it commutes with that. Right? And then 0, 0, 0, that's another one. The third one would be 0, 0, 1, 0. Right, this forms the basis of SL2C. What does B bracket with X do? It takes this to itself. What does it do here? I think it probably switches the two. No, sorry. No. It takes this one to plus or minus itself. I think itself. And this one to minus itself. You conjugate. Right, what do diagonal matrices do? If I multiply on the left, the rows get multiplied with the entries. If I multiply on the right, the columns. Right? So rows get multiplied by 1 minus 1 doesn't do anything. Columns, 1 minus 1, this one changes. This one changes sign. And this one also. But anyway, it's certainly diagonalizable, right? It takes it to a multiple cell, so it's a diagonalizable matrix. So the rank is one-dimensional, right? Maximal abelian subalgebras are one-dimensional. But of course, anything one-dimensional is maximal abelian. It's just a one-dimensional space. Anything commutes with itself. Right, so any subspace of SL2C is maximal abelian. And from the real category, one would expect they are conjugate to each other. But that's not true because let's choose X as my generator X to be 0, 1, 0, 0. Let's choose that to be my element. It's, again, one-dimensional, generates something one-dimensional, maximal abelian. Right? Does it diagonalize? Is Rx diagonalizable? And I claim the answer is no. I'll leave it as an exercise. Just see how it acts on the Lie algebra and try to show you can't diagonalize it, no matter how I change the basis. How could you change that a matrix doesn't diagonalize? What's an example of a matrix that you can't diagonalize? So just as a matrix question, right? Nilpotent, right? So if you have a diagonal one, of course, then you have these eigenspaces. The matrix preserves the eigenspace. If I iterate, it still preserves the eigenspaces. If it's nilpotent, everything goes to 0. So the nilpotent one can't be diagonalized. And I bet this one is probably nilpotent. So I'm pretty sure. So that's an exercise. So what needs condition B? Otherwise, the theory doesn't work. And then there's an element of the maximal, an analog of the maximal torus theorem. So if H inside G is a Cartan subalgebra, and the following hold. If X, so I can, what does it mean I can conjugate everything? If X lies in G, I don't have a group now, but G is a complex Lie algebra. It's a complex subspace. what's the analog of the adjoint if I just look at the Lie algebra? If I don't know the group, how would I do that? Right, if I have a group, I have at G, or maybe say at G, right, goes from G to G, of course, derivative conjugation. But if I don't know the group, how can I describe that? What kind of endomorphisms are those? We've seen that. So the set of all such things, all such linear isomorphisms, it's a group we've seen before. That was int G. Right, we had out 2 the set of all endomorphisms. We had int G, and int G could be seen as the image at G. Right. In fact, this here was an isomorphic to G mod the center of G, if you want to. But that's what this Lie group looks like inside out G. The inner automorphisms. Where G was connected, so here we assume G is connected. So if you want to, that can be your definition of int G. But it actually doesn't depend on the group at all. It's just the concept of the Lie algebra. In fact, the way one can define it, if I don't want to talk about the group, what would be a good way to define it? By the Lie algebra. Right. What was the Lie algebra of the automorphism? Was the derivations. And what's the Lie algebra of int G? Inner derivations, but what do they look like? Yes, they are the set of all at x, where x lies in G. And that's a subalgebra inside the derivations. And this is simply the subgroup inside this group, which corresponds to this Lie algebra. Right. So if I form it like this, I don't care about the Lie group. I can just do it like that. Look at the Lie algebra of all inner derivations like this, and look at the subgroup inside out G. So for example, I could say then, well, int G is generated by things of the form e to the ad x, where x lies in G. All right, so how would I argue? Well, this is just a matrix group. Exponential map is e to something. This is my Lie algebra. Ad x lies in Lie algebra. I take e to that, I'll end up in the Lie group. Of course, in general, I can certainly get something close to identity like that, but not necessarily the whole group. But certainly, this contains things of this contains a neighborhood identity, and then it generates everything. But not everything may be exactly of that form, but everything generated by that. Okay, so then the statement would be here, then there exists an A in int G such that A applied to x lies in H. So I can get everything into the Cartan subalgebra with something inner. And if I have 2 of them, these are Cartan subalgebras. Then again, there exists an automorphism, inner automorphism, such that AH1 is equal to H2. Particularly, I can again call the dimension of this H the rank of G. It's now well defined by this theorem. That's a non-trivial theorem, more difficult than the maximum rank theorem, unfortunately. But I'm not going to prove it. Maybe one more addition to that, which is important for us later on, that the normalizer of, let me write like this, the normalizer in G of H is equal to the centralizer in G of H is equal to H. So that's the last statement. So what does that mean? Centralizer are things that commute with it. So here I'm saying that if x comma h is equal to 0, this implies x and h. But the first one is even stronger than that. If x comma h, so comma, so h, oh, it doesn't matter, let's call it h lies in h, but not necessarily identity, it also implies x lies in h. And of course, if it does, then that's the identity, right? There's nothing in the normalizer except for the trivial thing. So this property is kind of the analog that we saw for a compact Lie group, where we said the normalizer of a torus, mod the torus, is finite. That means Lie algebra is trivial. Normalizer of the normalizer of the algebra. So in the maximal torus case, that's exactly what we proved. The normalizer of the maximal Abelian subalgebra is the maximal Abelian subalgebra. Okay, so that's the analog of the maximal torus theorem for complex Lie algebras. That's not so easy to prove. That's a tricky proof. I'm not going to prove it, but I just make the following simple observation that say if K is compact, say semi-simple, that's not so important, and T contained inside K is maximal Abelian. So our previous setup, then when I complexify, inside G tends to C is a Cartan subalgebra. And that follows almost immediately from properties that we know for the real one. Let me just indicate kind of what the only thing you have to observe is. Like, why is it maximal Abelian? Well, things in H are now the form x plus iy. Right? That's the only thing I have to worry about, that I have both a real and an imaginary component. But if x plus iy commutes with pardon? Okay, what K is my compact Lie algebra, or I complexify the compact one. Thank you. So I start with one, a real one, which is compact. G is inside, K is inside G. Okay, thank you. It didn't make sense. Absolutely. So I start with a compact one, a real one, compact, semi-simple. Inside K, I look at the maximal Abelian subspace. Thank you. Then I complexify both. So I take T tends to C, inside K tends to C. This would be my G, my complex Lie algebra. And I claim this inside G, the complexification is my Cartan subalgebra. So, thanks. So if something commutes with H, in particular it commutes with, say, a vector Z which lies in T, and of course this is xz plus iyz. But if that commutes, or if it commutes with it, of course then each one must be 0. That must be true for every z. So x must commute with everything in T, therefore it lies in T. Y also, so y lies in T. So x plus iy lies in complexification. So just break up everything to real imaginary part, and it drops out. So So this theorem is easy if I think of complexifications of compact real algebras, and it's very easy, right, and geometric. Later on, we're going to see, well, can one maybe use that to give a purely geometric proof of this fact? We're going to prove later on that if I take a complex semisimple Lie algebra, of course, this was our general assumption, right? G is complex and semisimple in this theorem. So I take a complex semisimple Lie algebra. We're going to show it has a real form which is compact. So it actually is of this form. Right? Every complex semisimple Lie algebra must be the complexification of something that's compact. Okay. So once I prove that, it sounds like I proved the theorem over there. Unfortunately, to prove that it has a compact real form, I use that theorem. So it's a circular argument. But at least this is good enough now for us that we have some understanding of why one expects that to be true, and why one has this additional condition, part B, here. Of course, notice that in this case here, it's automatic because ad x is that's ad x plus I at y. Okay, so that's maybe another trick. Why does this diagonalize? I have to show x ad x plus iy diagonalizes. Ad x does, ad y does, because they're skew symmetric, so when complexify the diagonalize. But in general, if I add two diagonalizable matrices, they don't have to be diagonalizable. Right? That's in general false. So what do I have to add? If they commute. Right? So what's the commutator of ad x and ad y? These are inner ones, right? It's a subalgebra, it has to be inner again. So it should be again of the form ad of something. And what could it be? The bracket. This was one of those nice simple facts that follows from the Jacobi identity. Because this is now equal to 0 because x and y lie in the maximal Wien subalgebra. They commute. So indeed, they're diagonalized, commute. I can diagonalize at the same time. So this one also is diagonalizable. So that's the only trick I have to add. OK. So we have these Cartan subalgebras. And we always know that these can be diagonalized. And that's what we're going to want to use next. What does that do for us? And the standing assumption the next couple of lectures is G is always semisimple, complex semisimple. So for x in H, I can diagonalize ad x. But as we saw over there, if I take two vectors in H, then I can diagonalize ad x and ad y at the same time. So each one breaks up into one-dimensional eigenspaces with respect to the same basis, right? For all x and y inside my maximal Wien subalgebra. So I can write G as a sum of eigenspaces, sum of common eigenspaces. Because the eigenvalue changes with x. Right? They're the same basis of eigenvectors, but the eigenvalue will change with x. And now we want to organize that in terms of what are called roots. And understanding semisimple Lie algebra is all done via roots. So if I think of the eigenvalue, so of such an endomorphism at x depends on x, I could call it alpha of x, right? Notice that when I add two x's, so first if I multiply x by a constant, of course your eigenvalue changes by a constant clearly, right? If I add x and plus add y, it's I get alpha x plus alpha y. So this must be linear. So each eigenvalue of such a matrix must be a linear endomorphism. So that justifies the following: let alpha be a linear a linear map like this, something in the dual space. Then I call G sub alpha the eigenspace. So x in G such that all of these are eigenvectors. So such that h comma x is equal to alpha of h times x for all h inside the Cartan subalgebra. So here, I guess here x and y were in h, right? It's kind of convenient as my general convention. I'm going to call vectors in G, I'm going to call them x and y. Vectors in H, I'm going to call H, H1, H2 if I need them. That tells me kind of visually where I sit, whether I sit in the Cartan subalgebra or in all of H. So these are my eigenvectors, right? And here I look at the whole eigenspace, which might be something that has dimension bigger than 1. But later on, we're actually going to show they're one-dimensional. That's not obvious at all. So in other words, actually the whole Lie algebra splits up into some of one-dimensional eigenspaces. But certainly at the moment, what is clear is that G is equal to H plus the sum of the J alphas. If G alpha is non-zero. And in fact, I can think of this H. I claim H is the same thing as G sub 0 as a zero eigenspace. Right? What does it mean if alpha is equal to 0? What would that mean? Set of all x that commute with everything in the Cartan subalgebra. And these are all 0 for all h's. Well, that implies, by what we just said, that means x lies in h. Okay. And if and only if, right? Of course, the other way around also. The centralizer of h was equal to h. So h is just G0. Turns out that 0 is not counted as a weight. It's not a good idea to count it as a weight. And we can just think of this here as our zero eigenspace if you want to. Oh, it's not clear at all. No. It's going to take us a little to prove. Right? Okay. So this decomposition now is clear by what we said. Right? It's kind of clear I can do this, and that's our starting point. The alpha where G alpha is non-zero, because in general, of course, I expect most of them to be 0. After all, they're only found in the eigenspaces. Then alpha is called a root, and delta is a set of all roots. So another way to write this then, a more common one, this is H plus sum of G alpha, where alpha is in delta. I should add alpha not equal to 0, but usually that's my assumption. 0 is not a root. Just as convention. Right? So then I wouldn't have to add that. A convenient convention. So now I want to understand these functionals. Right? So delta is a subset of the dual space, a finite subset. I find many roots. I want to understand the geometry of these finely made elements inside H star. Right? Do they span H star? What's their angle? What's their length? What's the geometry? A complete understanding of the geometry. And it's very, very restrictive, the geometry of these vectors inside H star. Often we identify H star with H by using the killing form. Right? We know the killing form is non-degenerate, so you might as well use it. A little bit careful, it's complex valued, right? Bx, x is not real, because it's skew-symmetric, not skew-Hermitian, right? And of course, there are vectors where bx, x is equal to 0. Vectors can have 0 length. So it's a skew-symmetric complex bilinear form, so we have to be a little bit careful. Anyway, so what does isomorphism look like? Say if I take a vector x in here, for example, then I send that to, I'm usually going to call it h sub x. Well, let's call it, send it to alpha, where alpha is what? So how does this duality with an inner product go? I take an inner product, I characterize what it does for any y. And what should it be? Alpha of x. Right, so that defines a functional. For each x, what's alpha of x? Sorry, am I doing this right? X is y. Right? I want to tell you what the functional is that corresponds to this vector here. I apply it to a y, and what is it? It's the inner product. Right? And of course, it's the other way around. If I do it the other way around, if I take a functional, that gets sent to something which we're going to call h sub alpha, just as a notation. Right? So alpha is something in a dual space. H reminds me I'm in the Katna subalgebra, right? And this reminds me it depends on the element in the dual space. And what does it do? So alpha applied to y, well, this was, of course, b h alpha y. Right, that's what this said right here. This also induces an inner product on the dual. So on H star, I also have an inner product now. I don't want to introduce too much notation. I'm going to give it the same name. So what would be, say, b of alpha beta? What should that be? So I have one on H. I have a duality of the vector spaces. I'm going to use a defined one on the new vector space. Because I use my duality to first go in the vector space and then take the inner product. Right? If I want to be picky, I should call that a star because it's an inner product. Right? And of course, what is this here? Well, I can now use this rule right here. It's the same thing as alpha applied to the vector. And the vector is h beta. So I can also do it the other way around. I can think of this as beta applied to h alpha. Okay. So all these are we're going to use interchangeably because sometimes one is more convenient than the other. So let me just unify notation. So I'm going to call the inner product on G by the usual inner product notation. I can think of this as B, the killing form, although I don't have to. Anything where at x is skew symmetric will do. So if I take any inner product where at x skew symmetric, everything will go through. But for the moment, you can think of the killing form. But in any case, I want to use a simple notation instead of b. So if I have vectors x and y in H, this is going to be the inner product. If I have vectors, say, alpha and beta in H star, I use the same notation. It's going to be alpha beta, using the notation over there. And then I use these equalities, right? This is equal to H alpha, H beta. This always means that alpha is a vector of my dual space. This is my vector in H, using the duality. And that's equal to alpha of H beta, or beta of H alpha. So I'm going to use the same inner product, right, on H and H star, and just give it this usual name. So this is something good to always keep in mind. That's how I compute inner products. Okay. So now I want to understand, write down properties of these root vectors. Some are very easy and some are tricky. There's one beautiful trick. That's kind of the root, the kernel of the whole theory, which I want to explain. But maybe as a reminder, let me write this up here. So you won't get too confused whenever I do that. But it's good to use them interchangeably. So you continue to keep that in mind. So here are elementary properties. If alpha and beta are roots, then the Lie bracket between G alpha and G beta is contained in G alpha plus beta. So roots just add. But I'm not saying that this vector space is non-zero. I'm just saying that if it's non-zero, then brackets of these must lie in here. They might be 0. So these roots are not additive. But they can't be, right? It's a finite set. You can't possibly add such vectors and get such root and get another root in it. So it may not be 0, but the brackets certainly behave like that. What are some other elementary ones? If they are non-zero, so if alpha and beta are roots, and alpha plus beta is also a root, then if it's non-zero, then the inner product between G alpha and G beta is equal to 0. So lots of things are 0. What does that say? The only way something can't be 0 if the sum is 0. That's kind of weird, right? Particularly G alpha with itself must have inner product 0. Inner product completely vanishes on G alpha. Right? They are all vectors of 0 length. So what does it mean? So here's a consequence, if you want to, that if alpha is a root, then minus alpha must be a root. Because the only way that inner product can be non-zero is if that beta equal to minus alpha. Right? Those are the only ones that can be not equal to 0. Everything else is 0. And of course, the inner product is not degenerate, so there better be something that gives me something non-zero with something in here. But if it does, it must lie in the space with negative eigenvalue. Of course, I should be careful here. I'm not saying yet that any vector in here with any vector in here has non-zero in the product, because I don't know yet what the dimension of these things are. If they're bigger than 1, this can't possibly be 0 for all vectors. So I can't say that yet. But certainly, those are the only possible inner products that can be non-zero. That's what it says. It's another elementary property. The set of all alpha, where alpha is a root, it spans H star. So it really fills out the whole vector space additively, if you want to. And E, killing form, the inner product, if you want to restrict it to H, is non-degenerate. Okay, so all of these are easy. The only one where I have to argue, well, let's do this one. It's not so hard. What does it mean? So here's another useful notation I'm going to use if I take a vector in G alpha, I'm going to call it X alpha. Because the vector is not unique, but it reminds me where it lies. That's a very convenient notation. If I take a Lie bracket between such two vectors, I'm supposed to show that in this root space here. How do I see root spaces? By taking Lie bracket with anything in the Cartan subalgebra. And now I can use a Jacobi identity. Right, bring it here. And then put add H in here also. Oh, but now you can see how it goes already. Right? X alpha is a root vector. Alpha is a root applied to here. So I get alpha of H of X alpha Y beta. And here, this is a root. Y beta is a root. This becomes beta of H, X alpha plus X beta. So it's alpha H plus beta H times the Lie bracket. Okay, that means this. So just a co-identity. So why is B true? So this is just A. Let's see. What was the trick there? Ah, yes. Now I have to. Now I'm going to use what the inner product looks like. I'm going to use a killing form. What is inner product between x and y? Its trace of at x at y. So what does now we assume that say I have a vector x alpha. In G alpha, I have a vector y beta in G beta, and alpha plus beta is not equal to 0. What does I want to compute the inner product between G alpha and G beta. So I have to look at the trace of at x alpha composed with at y alpha, y beta. What does at x alpha do? I claim part A tells me what it does. It tells me where all the root spaces go. It maps G beta into G alpha plus beta. I just add the root alpha. That's what it does. So where does it go? Where does it take H? H, I'm supposed to think of the 0 root vectors. It takes it to G alpha. And where does it take, say, G gamma? It takes it to G gamma plus alpha. Now I'm supposed to compose that with at x beta also, or y beta. So what I did do, let's do both at the same time. H goes to G alpha. I take a Lie bracket with beta. This goes to G alpha plus beta. You can also see why this, whether it's 0 or non-zero is going to enter somehow, right? Where does it take G gamma? Well, here I add alpha. I do it again. I add beta. It goes to G gamma plus alpha plus beta. So if alpha plus beta is non-zero, this always goes into a different vector space. Right? If you want to write it in block form, where H, G alpha, G beta, and so on are the blocks, right? Then in each block, it gets sent something below that block, or above that block, right? But there's nothing in the diagonal if this is non-zero. So then the inner product must be 0. If it's equal to 0, of course, then it doesn't tell me anything. It preserves G gamma. G0 is H, so it goes from H to H, G gamma to G gamma. It just preserves all the root spaces. Okay, so that certainly won't be 0. So I already said why this has to be true, but that's not degeneracy, because these are the only possible non-zero inner products. Why do they span H star? Well, so if not, there exists, say, a beta in H star such that they are orthogonal to all the other things for roots alpha. So what does that mean? Remember, this here I can view as inner product in H alpha and H beta, or as beta applied to X alpha, or the other way around. Let's see which one do we want it. What are we trying to put at this span? I don't think it matters. Okay, this is 0 for all alpha. What does that mean? So now we look at our root space decomposition here. It would contradict the fact that B is the Killing form is non-degenerate. Maybe you want to do it the other way around. How about I can choose, right? It's either way. Beta is fixed, right? Beta is my fixed element that's orthogonal to all the other roots. Look at the vector that corresponds to that dual element inside the Lie algebra. Every root vanishes on there. Right? So all these things vanish on there. Remember that what was G alpha? Instead of X alpha now, let's write it like this, where H X alpha is equal to alpha of H times X alpha. So if alpha of a vector is 0, it just means it commutes. So this here means that H beta commutes with all G alpha. For all alpha. That's what this here means, right? Well, so it commutes with, and we had this decomposition, right, of the whole vector space was H plus the sum of the G alphas. So here it commutes with everything. This, of course, is abelian, so it commutes with everything. So this implies that H beta lies in the center of the Lie algebra G. But it's semi-simple, so the center must be trivial. So it can't be. So they really span things. And E is similar. Maybe I want to E. Let me write down the essential things we're going to have to do on Monday. Maybe I can explain one trick a little bit. So what's more difficult? For example, that dimension is equal to 1. That's tricky. Surprising also, it's tricky that roots have non-zero length. That's tricky. So remember, everything in G alpha and G alpha has 0 in a product. So vectors in G alpha have 0 length. But the claim is that alpha here, of course, alpha lies in either H star or its dual lies in H. It's the same thing as saying H alpha is not equal to 0. Right. So they're called root vectors often. They have non-zero lengths. All X alphas have 0 lengths. So that's something we have to prove. And then we'll also prove that if I look at a Lie bracket between X alpha and an X beta, where alpha and beta are roots, then this is equal to the inner product between X alpha and X beta times H alpha plus beta. No, sorry. If I take a root, look at these inner products, these Lie brackets, I get this value. So in other words, the important thing here I'm trying to say is that G alpha, G minus alpha, are all multiples of the vector H alpha. So it's one-dimensional, and it's simply H alpha. And the multiple is given by the inner product. Because remember, we said that in general, these inner products can be 0, right? So you can only expect something like this for X alpha and X minus alpha. So these are 3 important properties one has to prove. And well, maybe time's up. So the trick that I'm going to explain on Monday is that I look at subspaces inside the algebra G, which are things of the form the sum of G beta plus n alpha, where I go over all alpha in Z, and beta and alpha are roots. So fix the beta and add any multiple of alpha. They may or may not be roots, so this vector space here is typically 0. And of course, this set of roots is finite anyway, so this will be a finite-dimensional subspace inside G. And I look at how does AdX act on this here. So sometimes AdX preserves this subspace. When it preserves it, I can take a trace. When I take a trace, I get some information about inner products between n and alpha and their roots and what n's are allowed for this to be non-zero. So the main trick in the rest of the discussion when I prove properties to look at vector space of this form. For appropriate choice on beta and alpha, I look at vector space of this form, and then I take traces and get all kinds of conclusions. And these are all of this form here, and they're not obvious, unlike the ones over there, which I think I consider obvious. OK, and then we continue with Dynkin diagrams. OK.